former PhD students, Dan Gildenbesher and Celia Lopez, wrote a fairly substantial review article on secondary atomization that was published in Experiments in Fluids. And a lot of what I will talk about is based on that review paper. And then the remainder of what I'll discuss is work that has been done since then, primarily at with also some collaborations, some very significant collaborations with students from the Institute for Thermal Machinery, Karlsruhe Institute of Technology, which we all used to know as University of Karlsruhe. Okay, next slide, please. So since this is a specialist meeting, I won't go into a long-winded description of secondary atomization. I think we're all familiar with the concept. And we could debate perhaps that there are 5 different methodologies of the secondary atomization process. Not all authors agree with these particular modes and these particular values, but for the sake of discussion, we're going to just assume that we have the so-called vibrational mode, bag mode, what's called multi-mode, which used to be called bag and Stamen in some quarters, sheet thinning, which in the early days of this subject was called shear thinning, and then catastrophic. The Weber number ranges are values that are approximations or at least reasonable estimates of the Weber number at which the process shifts from one of these modes to the next. So you can see that about 11, 35, 80, about 350. And if we can go to the next slide. So we'll start the discussion by talking about the vibrational mode. These is for particularly low Weber number values, and essentially under this conditions, the drop oscillates at something like a natural frequency. If you are familiar with Lamb's hydrodynamics, he actually shows how you can calculate the normal modes in this sort of situation. If there is enough time allowed, the drop will break up into a few daughter drops, 2 or 3, maybe 4, but are all roughly the same size. But the one thing is, the practical thing is the break time is long for the vibrational mode compared to the drop transit time, the typical drop transit time to the spray. So as engineers, we are usually not so interested in this. All right. So here we have the breakup mode, which is for all of the practical modes of interest. It's the lowest Weber number range. It's called the bag breakup mode for obvious reasons. We have a cross-sectional cutaway view here on the right that shows the drop deforming into a bag with a thickened rim, the upstream edge. The back and one from the rim, and there are different sizes because of the characteristics, different sizes of the two parts. And so you often get a bimodal distribution. Nope, I'm back. So, okay. So let's go on to slide number. So one of the things that's not been known with certainty before is what does the local fluid mechanics structure look like around the drops as they evolve? And on this slide, we have a couple of sets of PID images that were taken by students from the Institute for Thermal Turbomachinery at the Karlsruhe Institute of Technology when they were visiting at Purdue in late 2010 and early 2011. And if we look at the left-hand side, we can see the drop undergoing distortion. So we'll go across the top row, then down to the middle row, finally down to the bottom row, left to right in each case. And if you look closely at the images, you can actually see something that looks a little bit like a low-pressure zone on the backside drop due to the recirculation, the gas recirculation. And that low pressure zone is likely part of the reason why the bag extends downstream as it does. You can also see the prominent rim, right-hand figure of the batch of 6. That pretty clearly explains why we get a bimodal distribution of drop-size fragments. And then if you look over to the right-hand side, there we have a number of realizations of the PIV measured velocity field behind the drop. And if you look at the lowest of those images, you can actually see some evidence of recirculation and vortices being formed, which lends credence to the fact that there's a low pressure region behind the drops, which is assisting the breakup. Okay, on to slide 7. We'll now increase the Weber number to the next range of drop breakup geometries, the so-called multi-mode, or what we refer to as bag David mode. Similar to the bag mode, the behavior is the formation of some sort of downstream protrusion. But in the multi-mode situation, we have this upward stain, is called by earlier workers in the field. The breakup process occurs by the bag rupturing. The rim then breaks up second. Stamen then breaks up at the end. You end up with large size fragments from the rim breakup and the stamen breakup, small size fragments from the bag breakup, and other bimodal size distribution. The last piece of information from this slide is shown at the lower left, and it provides the geometry for an instability analysis that might possibly be an explanation for why we get the transition from bag multi-mode breakup. And there are some characteristic dimensions in there: the cross-stream dimension, the wavelength of the maximum fast stability mode, the direction of flow. And if we go to the next slide, we will see that the results of the stability analysis tell us that the maximum growth, the maximum growth rate disturbance scales as cross-stream distance, drag coefficient, Weber number, like shown. Right? So the real point of this particular slide is that for the range of Weber numbers typical of multi-mode breakup, which is from 35 to about 80, we don't get particularly good agreement between linear stability analysis for the number of cross-stream wavelengths and the disturbance and the actual Weber number. We notice that we're getting somewhere between 2, which is good news, but we get out to Weber number of 80 to around 5 or 6 nodes, and that's not what we actually observe in an experiment. So if we go to the next slide, what we have here is something very similar in terms of the PIV images that we saw for the bag breakup mode. And again, if we start at the top, we'll cross each row to the middle and then up to the bottom. The left-hand figures show, again, the presence of some sort of recirculation. And it appears that there is something of a backflow that's occurring as well. And the Karlsruhe students took all of these images and then post-processed them. And after you take a number of realizations, you can see the information in the right-hand column. So as we move downward, you'll see some strong recirculation zones form, and eventually, near the bottom, when the stamen is starting to push its way back upstream, we get considerable recirculations at the top and the bottom. Right? And so this is now looking like the multi-mode breakup geometry is due not to transverse stability, but instead to some blank fluid mechanics that are occurring in the leeward edge of the droplet as it deforms. Okay, on to the next slide, please. The next mode, the so-called sheet thinning, or what used to be called shear stripping mode, was a point of controversy for quite some time because early work by Ranger and Nichols indicated that this was actually a viscous-dominated process, and that it was a boundary layer stripping, a viscous boundary layer stripping mechanism for the gas flow over the top and bottom of the drop. But more recent work by Reitz and his colleagues up in Wisconsin showed that, in fact, that's not what happens. It's more of a flag waving or a flag flapping mode where the dynamic pressure pushes liquid out the perimeter of the top, eroding the outer surface. There's a coherent residual drop that exists eventually, and the fragmentation distribution are lots and lots of very small fragments with perhaps one big piece that remains in the form of an intact core. Okay, on to the next slide, please. Finally, there is the so-called catastrophic breakup mode. This mode has been investigated significantly by the late, for heaven's sakes, late Dan Beaver, who had a very high Reynolds number, high Weber number shock tube at the University of Minnesota. And it was now also subject to some controversy because some of the work that was done in that group strongly suggested that this was a transverse instability mechanism that was corrugated the leading edge of the drop with large amplitude, fairly small wavelength disturbances. Those disturbances effectively polarized the drop and gave a mist of extremely small fragments and surrounded a core of larger fragments. The subsequent large fragments also may have broken up later on downstream, but the prevailing thought was that it was a transverse instability. Theophanis doesn't agree with this particular interpretation and is proposing explanations of his own, but I'm not going to actually go into that this afternoon. Okay, so the next slide, please. All of the information that we've seen, at least in terms of the Weber number boundaries for the various breakup modes, can be correlated onto this single plot that was developed over a number of years by Faith and his workers. This is an extremely valuable piece of information for both scientists and engineers because it gives indications of under what conditions we would expect drops to deform. So where we would expect to be able to make measurements, for instance, with a phase Doppler analyzer, and then also under what conditions we would expect to see oscillatory deformation, bag, multi-mode, and you can see this is an old plot because the top mode there is called the shear breakup, which we would now refer to as sheet thinning. One other piece of information that is notable for this figure is that if you notice a Zorga number of about 0.1, these low boundary lines all begin to upward and to the right. The Zorga number of 0.1 is when viscous effects to become important. So the key takeaway from this is that all of the work that was done for gas turbine engines and internal combustion engines, which is very valuable in its own right, is not going to be directly applicable to practical fluids of much higher viscosities, as paint, coatings, foodstuffs, medicinal sprays, and so on and so forth. Okay, next slide, please. In addition to understanding where the mode boundaries are, the breakup boundaries are, if we were doing computational work for expert application, we would also be interested in some additional quantities, the so-called breakup times. A number of them will be presented down a couple of slides, we are also interested in the droplet size at the end of the secondary breakup process, wherever that might be. And of course, for computational purposes, we also would like to know fragment positions, velocities, accelerations, both the position, velocity, and acceleration of the initial drop itself in an intact core. So on to the next slide. So we'll define some times here that are fairly universally agreed, close to that for a disk. Processes. This is a better method than just simply applying Newton's. Next slide. Oh, sorry. On to the next slide. It's over this breakup. Came up with an expression for the velocity of the core. Okay, so the velocity of the unbroken core relative to the initial velocity drop, and written in terms of an average breakup, some continuous time breakup is over. It also provided the velocity of the fragments, which is the second one down, in terms of the velocity. That's what I might expect. The fragment velocity should be higher than that of the core because they are aerodynamic to inertia effect, they would more rapidly approach velocity. On to the next slide. Now the time to make comments about the size distribution of the fragments, which you might call the daughter droplet. And in slide 24, the approach that had been evolved from that of Erdmann, who knows the diameter of the fragment max, and then about the empirical evidence that roughly double the of the fragment size distribution. Now, it looks at on the surface like there are two unknowns to the situation, but it turns out they discovered that the maximum max could be approximated by a simple aerodynamic analysis, which is shown on slide 25. So the daughter drops don't accelerate in next slide, we see that we can relate that maximum size called critical Weber number, something around 11 or 12, the bag breakup node, in terms of mass density and the of the daughter droplets. Now, the problem is that the daughter droplet speed, the fragment speed breakup is not equal to the initial. Yep, we're back. Catch the discussion on slide 26, or did that get chopped off?
No, we are on slide 26.
Okay. So when we look at that expression for the maximum stable diameter, its weakness is that the velocity of the fragments at the end of the breakup process is not equal to the initial relative velocity. So that has to be compensated for. And if we go to slide 27, you can see one method for going about that. In this particular situation, what's been done is that a little bit of algebra has been performed in that numerator. And so we've replaced the initial droplet velocity relative to the surrounding gas with its actual velocity at the end of the breakup process. The difficulty now is that we have this sort of new unknown V drop that needs to be computed, but we have information on how to do that from other work by Pilch and Erdmann. Oops, wait a minute. And so we can actually take the total breakup time, insert that back into correlations for the drop speed at the end of breakup, calculate the maximum diameter, and use that then to estimate or to provide information about the fragment size distribution. If we go to the next slide, there is an alternative approach. Now this is due to Faith and coworkers, and it makes use of a boundary layer analysis, which has fallen somewhat out of favor since the work of Reitz back about 10 years ago. But since it's a correlation, it can be used for practical computations. One just has to realize that the underlying physical explanation is probably no longer accurate. It also makes use of an empirical fact that Hal Simmons discovered some 35 or so years ago, and that is that for sprays where secondary atomization is important, the mass median diameter divided by the solder mean diameter turns out to be about 1.2 for an awful lot of practical sprays. So if you use that extra piece of information and then the boundary layer approach that Faith has proposed, you can end up with a correlation expression to get some information about the fragment size distributions. All right, and by the way, that slide 44 is no longer the right number. We should change that to slide, where did it go? So now it's actually slide 22. All right, on to, it worked about 15 years ago, proposed a different expression for the bag breakup. And he suggested that the ring breakup was due to toroidal instability weighing, which in fact now, with recent experimental results, looks to be exactly the case. And one can then find a value for the Weber number for the fragment size distribution in terms of a total time and an initial time, and correlation coefficient or a pre-multiplying factor of 0.32. And then the initiation and total times come from earlier slides, which are actually slide 17 for the total time and slide 15 for the initiation time. Okay, now a different way, and perhaps a better way to do this is just to go out and measure the darn size fragment distributions. So on slide 30, we have an image on the upper left of aerodynamic breakup as a bag breakup incident for a drop. And the image on the right, on the upper right, is in fact the fragmentation products. You can see quite clearly the two significantly different sizes of fragments. There's an outline of the rim with a number of large fragments that perhaps supports Wirt's contention that the rim breaks up due to circumferential instabilities. But Frank Oliver Bartz, who was here from ITS at the Karlsruhe Institute of Technology, put a PDA measurement plane downstream and let the experiment run until he had a somewhat statistically significant sample of fragments. And you can see that the fragment size distribution, as you go vertically up and down that PDA measurement plane. Now these drops were, the initial drops were fairly large. They were about 2 millimeters, 2.5 millimeters in diameter, which is why the solder mean diameter of the fragment distribution is greater than half a millimeter. But the key points here are is that, first of all, the fragment size distributions can be measured. This is the first batch of measurements to do that, as far as I know. Then the second thing is that there is a spatial variation in the fragment size distribution, with the largest fragments being located in the region, the annular region, where the rim breaks up, and then the smaller ones in the core where there are less rim contributions. Okay, so if we go to slide 31, here is some more recent work in concert with ITS at the Karlsruhe Institute of Technology. The equation at the top is a nonlinear tab model, nonlinear Taylor analogy breakup model, that was developed by Schmiel when he was a PhD student in Karlsruhe some 10 or so years ago. And the picture here actually shows computations, comparison of the computations between model predictions by, first of all, Schmiel, which are the blue lines, Frank Oliver Bartz, when he was here, which is the, let's call that violet line, the original Taylor analogy breakup model that Amsden and O'Rourke proposed, which is the red lines, and then a wave breakup model line. And superimposed on this series of model predictions, you can see a fragmented bag breakup drop, sort of the right center. And then the black line is a curve fit, a piecewise curve fit, to the approximated center of mass of the drop as it accelerates and as it fragments. So the point from this is that the nonlinear Taylor analogy breakup model, as originally proposed by Schmiel, but most recently modified by Frank Oliver Bartz and Yildmesher, folks at Karlsruhe Institute of Technology, does a pretty good job of predicting the trajectory of bag drops as they undergo bag breakup, deformation, and fragmentation, and so on and so forth. Okay, next slide. So everything I've talked about so far is basically then for Newtonian liquids, classical things like aviation fuels or IC engine fuels or water-based substances or so on and so forth. But one unanswered issue, at least up to a few years ago, was how did the secondary breakup process change for Newtonian? That says on-Newtonian, but it obviously should say non-Newtonian. For non-Newtonian liquids. And there are two major topics here, the inelastic non-Newtonian liquids and then the elastic ones. And the next few slides will talk a little bit about the some recent results on the inelastic non-Newtonian drop secondary breakup. So on to slide 33. So here we see some results from Celian Lopez's PhD thesis of about, maybe it's close to 2 years ago now. Let's look at the right-hand figure first. You may remember that that's the one that Faith put together with his students through many years worth of work. It's appropriate to Newtonian liquids. And the red and blue lines that have been superimposed on it show the range of conditions that Celian had considered in her thesis work for inelastic non-Newtonian liquids. So if we shift from the right figure to the left figure, what we have is a small segment cut out of the secondary breakup mode map with the Weber number on the vertical axis and the Onnes-Organ number on the horizontal axis, and the red symbols denote the multimode breakup observations, the blue symbols denote the bag breakup observations, and then the different shapes were for different formulations of these inelastic but shear thinning liquids. And the good news from all of this is that the behavior looks similar to what we see for a Newtonian liquid, and as long as we are careful to apply the correct rheology for the non-Newtonian inelastic case, as we'll see in the next slide, we can make use of work that has been provided for us in the past. So if we go on to slide 34, there were three main aspects of the original Taylor analogy breakup model that Sojka incorporated. One was to replace the original Newtonian shear viscosity by a power law effective viscosity. The second was to allow the time dependence of the drop velocity, which means the distortion is going to be occurring at a different rate than predicted by a case where the drop velocity does not change. And then the deformation of the drop radius was written in terms of some dimensionless groups. And from this particular equation for the motion of the drop and for its deformation, which is shown under the Liu et al. Correlation, we'll go to slide 35. All right, we'll go quick over slide 35. This is just the non-dimensionalized equations for the drop deformation and for the drop velocity. So let's go to slide 36. So here we have two figures that are showing the initial breakup time. Remember, that's the time when the drop ceases to be an oblate spheroid or close to an oblate spheroid. And we have two different sets of data. In one case, we are changing the inelastic non-Newtonian behavior by varying what's called the consistency index. And then in the other case, we're varying what's called the flow behavior index. Regardless of that, you can see that the predictions from this TAB model with the modifications I just discussed give us qualitatively correct behavior compared to what we see for experiments. And the quantitative agreement is not too bad. I mean, we're within probably 40 to 50% at the worst case. Okay, then on to the, let's see, that was 36, right? Now let's go on to slide 37. So on slide 37, we're actually showing predictions for the maximum cross-stream diameter, at which point the drop is no longer an oblate spheroid. Again, we have the two different categories of non-Newtonian inelastic liquids, and you can see that this simple model does an even better job of predicting the cross-stream deformed diameter than it does of predicting the initiation time. All right, and I think the next slide is the last one. Yes, so what next, right? Well, we've done some work and made some progress on non-Newtonian inelastic liquids, but the elastic liquid problem still remains to be considered, and that is considerably more complicated because you have an extra, essentially, degree of freedom in the rheology. We've just begun to start on fragment size and velocity distributions. There's quite a bit of experimental work to be done on that, and of course some companion theoretical or analytical work to be done as well. And now it has become possible with computational power to do single drop computations for deforming and fragmenting drops. If you're interested in that, David Schmidt at the University of Massachusetts has been making some significant contributions in that area. If you're, like I said, if you're interested, you could look at that. And that, I believe, is the last slide. So if there are any questions, I would be happy to try to answer them. If they get to be too difficult, I will just turn off my computer and go home and back to bed.
Turn on the video now, I think, Paul. I think it's nice.
Uh-oh.
Can you see us?
Yes, there I'm back.
All right. Can you turn on your video as well? We'll try that. We got some increased bandwidth thanks to a little 5-foot cable here.
Yeah, it's saying the connection between you is too slow for good video, but I'll keep it on.
All right. We said we have time for a few questions. Anybody that wants to ask a question needs to sort of come up here because the microphone is on here. Or I'll be happy to relay it.
I think everybody wants to go home.
Well, what was the temperature outside when you came in?
Well, if we just look at the numerical value, probably about the same as it is there. I think it's about 40 degrees, and it's not exactly pissing down rain, but it's raining.
Well, was there white stuff on the ground?
Nope. No, it hasn't been quite cold enough for that. It's been pretty strange. We're getting some kind of weird warm front moving through, and so we're just no snow, lots of rain.
All right. I think well, we had just to sort of summarize, we had a good couple of days yesterday and today of some talks, a few talks, and mostly just sort of thinking and discussions over, in an informal setting over tea, coffee, and lunch versus a formal setting here across, around a table like this. Mostly focused on IC engines, a little bit of gas turbine sprays and combustion, and today we had a short discussion on what is missing in our understanding of primary and secondary application. So this talk sort of certainly is well timed for that discussion as well. And thank you for coming in at this ungodly hour for.
Well, it's not so bad. I get to go home and go back to bed, so it's not a disaster by any means.
Okay, well, that's kind of you to think of it in those terms.
All right. Well, I hope that you have an interesting, enjoyable banquet or celebration tonight. I plan to have mine this evening too because I'll have all my grades turned in finally, and I guess I look forward to seeing everybody when we convene at Purdue in about a year and a half.
Okay. Well, now that you bring that was going to be the first point of discussion. So, shall we sort of agree upon May, June 2013 at Purdue? Is that?
Yeah. So one thing that you might want to consider. I don't know how much. What's available in terms of travel funds for those of you who are coming from India, but if you manage to time the meeting at Purdue correctly, you could also take advantage and attend the ILAS Americas meeting, which is typically mid-ish May.
Mid-May, right?
Yeah. Now I don't know how that works with your schedules of things, but it's just something to think about. Yeah. So your semester may not be over then. I know ours is here at Purdue.
Okay. Well, so we'll have to sort of at least a group of us, a group of you actually, to NSF. So it's going to have to be some U.S. university lead sort of proposal here to put this together. Would NSF pay for Indian travel? Is that?
I actually don't know. I haven't looked at this to any extent lately, and to be honest, right now I've got an NSF major research instrumentation proposal sitting on my desk that has to go out by the middle or towards the end of next month. So I honestly don't know the answer to that question. Yeah, I'll just have to. I'll just have to look into it, I guess.
Okay, well, I guess in that case, we'll just have to figure two separate sources of funding, which is still okay. It's not
well, but I mean, the biggest part of the cost is the airfare. So to stay an extra 3 days in hotels with subsistence, I think is I don't see why that's going to be a big concern in terms of total budget.
right. Okay. All right, good. All right. Thank you again very much, Paul, for doing the talk today.
Okay? All right, well, have a good evening, gentlemen, and I guess for those of you from Purdue, I will see you when we return. All righty, bye.
When we started, I guess when we started this discussion yesterday at about 9 in the morning, we said there were two sort of overarching objectives. One was try and see if we can evaluate the literature out there and the industry needs and see where the real gaps are. And we've sort of gotten started down that path, but certainly not there yet. What we have done is identify teams of people that will look at specific issues and try to identify problem areas that we want to fill. So that was the critical reviews of the state of the art part of the vision. The second part is this proposal development. They're obviously related. I mean, no proposal will fly without really establishing a need for the problem. So as far as the second part is concerned, this is just a few opportunities that I was able to find in about 4 or 5 days of doing some legwork and asking around. I know there have to be other opportunities just based on, like a probability of filtering particles out type approach. But these are good starting points. There's no doubt about that. So what we want to do is just sort of think aloud about these opportunities and see what we can do together to take these forward. I think that would be sort of one way to crystallize all of the thoughts that we have around specific action items. I will start by saying that I know Milind initiated some email discussion on developing an NSF PIRE proposal. Do you want to add to that, or?
The only issue, that email discussion, I think Paul pointed out that one of the factors in this is PIRE. It's limited by number of submissions one university can submit as the primary institution. You can join in any number of such proposals. So perhaps we may have to do this at multiple places to see where this is accepted. And starting with probably Purdue, because the number of people here, there's a major thrust at Purdue. So trying that out first, and then perhaps other places.
You're talking of an internal competition first, yes, that this has to get through, right?
Yeah.
So can it be can we put together a proposal that can be put in all the internal competitions, yes, and then we can make a decision?
Yes, but
all is 1, 2, 3, 4, 5, 6 universities at least represented here.
No, but there's usually some serious competition within each university, because correct, these programs are, PIRE's budget typically is $4 million. So there are a lot of people who want to apply for this. So we may have to sort of strategically do this where we can. And correct, then once we have that foothold, then others joining in would be very easy. So.
Okay, so any thoughts on where would be the strategically ideal location to submit this?
No, as you said, I think we should try at all these places, and okay, wherever we get through, Then we decide. Yes.
Actually, I don't. I myself have I've written other NSF proposals, but not a PIRE. What is the sort of the expectation from a PIRE proposal? Is it is it a research program or do,
It is a research program, and there you have to very specifically identify areas of strengths that you put together by, by putting together a group that is global in nature. So you have to identify, what work will be done where, how this collaboration would be helpful, and at least make some case that, all of that work could not be done unless you have some partnerships like this. So that has to come through in the, and of course, having this workshop and having some collaborations would definitely help in
okay.
putting that together. At least that's what I have. I mean, I've gone through this, uh, program details and so on, and that seems to be the thrust where.
Okay. So if May 15th is the submission deadline for that, typically the internal competition deadline is about mid-January? Or
each university would be different. So
in some campuses, the internal competition deadline has already passed for that window.
I see.
And just recently, NSF reduced the number of windows that they have for different programs. So I don't know when, in the particular case of the PIRE, I don't know if they're going to have more than one per year.
Okay.
So that's something to find out first.
But certainly 6 months later there's another window, or is it an annual?
No, there was, the previous one was in October, something like that. When I started this email, that's when that first deadline was. So that. Yeah. I think October. So there must be two every year. October,
okay,
May.
Good. So then it's not so bad.
Yeah.
So, okay. So as far as that is concerned, would you sort of?
Yeah, I mean, I could coordinate this. I would be happy to, but there is no guarantee that it will fly through an internal competition at Cincinnati. So we just have to try.
I think I think we have as good a case as any. Yeah.
I think once we have a template,
yes.
we just put it in place.
Right.
Put it through the internal conditions that we have. Somewhere it went through.
Yeah, then we are.
Wherever it went through, and they understand.
Okay. All right. So good. So we'll look for some emails coming from Milind on.
I think the only thing you have to coordinate is that universities have different submission times, and you don't want to hold up another group that would be there. So it would be good to coordinate and know what the submission time is for the individual universities are, because otherwise if you're going to pull out of one, it's going to be a heartache for that university. So we should know what the submission times for all the universities.
From my side, I'll get everybody a list of everybody's emails with your permission, and so that way there's a network. Talk of network, slightly outside the scope of this. We're going to create a website that has basically like a wiki set up on it. Sujit has done this with, not Sujit, but Matt Juniper, right? You said, has done that for the instability network, where it's a forum for exchanging ideas as we move forward. So we'll try to do that in the next month or so. But email list is easy to exchange. The second opportunity that I was able to, that actually Sujit was able to identify, is the ONR NICOP, and I think the best person to talk about that is Sujit, because he has a grant funded by them. So.
Well, there is a ONR Global, that's where I got my funding from. So first you have to write a white paper. So I just wrote whatever I wanted to do and whatever I was saying. And then he said, okay, it looks interesting, and then why don't you make it a proper proposal? And then when that was interesting, he said, okay, fill up these forms. And these forms are very complicated, so I filled half of it, and then he was kind enough that could fill in the things which I didn't understand. And then it was sent to, I think, their headquarters in London, and then it got through. I was lucky because I didn't, it was a standalone thing without American partner. If you had Americans on it, chances are much higher. I understand that mine got through because I had a crazy idea. So, but I think, there's no specific deadline you can apply any time. That's what I understand. But we have to start with a white paper.
Do they only fund researchers in India, or would they fund counterparts also?
ONR Global funds anybody anywhere in the world. That's what I understand. And they like the ones together. Yeah, I mean, mine was like an exception, I think.
So maybe what we can do there is sort of identify 2 or 3 teams of people that are interested in pursuing that funding, just like the first NSF PIRE. Now, this is open competition, so it's not like there's only one PIRE that will go through one university, but each of us can write our own NICOP if we want. So that is a real opportunity. Like I said earlier, the program manager was here at.
And they fund fundamental stuff, so. But I doubt they're going to give me another project right away. So somebody else have to have their name on up top.
Okay. So maybe following this, we'll sort of try and identify teams. Now the template that Sujit put out with for the critical reviews is sort of like he says an arranged marriage that could also make some money for the marriage. So we'll either that or we'll try to find other opportunities. The same goes with the AFOSR. They have the same white paper system that they want partners in the US and in India. And the way I understand the Air Force part, if there is a PI that has an Air Force grant already, the chances are much higher. I mean, I'm sure this is the case with even regular AFOSR funding, that there's repeat customers are encouraged. But I think it's even more so with the global funding. And so, but even otherwise, that is also an opportunity. It's the same white paper system. You just have to prepare a 2-3 page white paper, send to the program manager in Tokyo in this case, and try to convince him that it is worth pursuing. The Knowledge Network Center, like I said earlier, is they are more of an exchange program. So if you want to send your students, or if you want to come spend some time here, or if you want one of our students to come there, or visiting faculty at your university for an extended period of time, we're talking 2 years, 3 years, several visits over this duration, they will do that. They will also, for that same duration of time, support conferences. So they'll support events like this. Like you could propose 2 events, one after the other, at some succession, and they'll support that. The brochure that is in your bags has more information on a website, at least, that you can go read up. That would be, but it's clearly not research funding. It is not funding to support graduate students for a long duration of time. So this is something that you can use as supplementary funding on existing projects. So this is what I've been able to identify. I think, of course, there is NSF has an Office of International Programs, OIP. I did write to the program manager, and they used to have a link with DST in India. I couldn't find that link, so I wrote to him to see if they're still working with DST.